So today we are going to see the DPD modeler, which is used, or the background is the dissipative particle dynamics method. And this DPD modeler is basically used for the phase separation simulations. Okay, so and for phase separation simulations, if we come on to the manual of the DPD modeler, this explains very well the calculations of the chi parameter, which is an very important parameter estimation with the help of the various methods which are possible here under the DPD modeler. The first one is the group contribution method, second is the Monte Carlo method, and thereafter the fragment molecular orbital method and molecular dynamics, and then the mixed system for the chi parameter interaction calculation. Okay, so the initial step is again the same as any other modeler that we have gone through. The first is the monomer modeler, where we model our monomers. Once the modeling has been done, we can take the monomers to the DPD modeler, and there we can get to calculate this chi parameter by various available methods. You can choose depending upon the accuracy you require and the computation power that you have. So the first option that we have to calculate this chi parameter is the group contribution method. Under the group contribution method, we get to calculate the molar volume and the cohesive energy. These two are available as a database. There is a specific tab is available. If you use the molecules from their sections, it will have the values of the molar volume and the cohesive energy for each segment first. And once you have calculated the molar volume and the cohesive energy for each segment, then we get to calculate it for segments as well. For example, if we have two monomers, monomer 1 and monomer 2, so we have to calculate the chi parameter between the monomer 1 and 2, which will be utilized here for the calculation. And it uses again the databases. So we have 4 database available. From the out of 4, you can choose any of the database that suits for your model. And suppose the model or the monomer that you have modeled is have some options are not available in the database. For example, molar volume and the cohesive energy is not available. You can go on to the next options which are available. For example, Monte Carlo method, molecular dynamics, or the mixed system calculations. So here again the same steps to apply the force field, do the molecular mechanics calculations, molecular orbital for each segment, thereby to calculate the cohesive energy calculations, coordination number calculations for the segments, and then the calculation of the chi parameter. While going through the software or the options which are available, I'll explain all these options and what are the steps that should be taken care of while doing the Monte Carlo method simulations to obtain the chi parameter. Similarly, molecular dynamics method is also available, but for that one pre-modeled simulation is required, which is amorphous structures of each segment separately, and that amorphous structure will be utilized here for the molecular dynamics calculation to calculate the solubility parameter for each segment separately. And to calculate the chi parameter, then again we will be requiring the amorphous structure, which will be utilized for the calculation of the chi parameter by molecular dynamics method. And one last option is there, which is a mixed system amorphous structures, which is again based on the molecular dynamics calculations, where we calculate it with the help of the again molecular dynamics only, and to calculate the cohesive energy, and at the end the chi parameter interactions. The end results of all these 4 methods is the chi parameter. The only difference is the scale, or you can say the accuracy, and depending upon the requirement also you can choose either of the method which suits better for you. Once you are done with the calculation of the chi parameter, you can go on to the modeling of the polymer, and once you have modeled your polymer you can create your input file, and then you can run the DPD modeler engine to get your phase separation structures of DPD file, which is a dissipative particle dynamics method. So this was all about the various methods which is going to be taken care in the coming description of or the options of the DPD. So to start with, let's open up to the J-OCTA software, and as you can see there is a DPD modeler tab is available. We have created a directory DPD hyphen tutorial under the directory of the video where I am recording all the options or all the modelers which is available here. Okay, so the first thing, as we saw in the manual, is to create the monomers first. Okay, so the same steps: right click onto the parent directory, go on to new monomer, and then again new. Here we get to choose the monomers. For example, right now I'll be following the manual here itself. So I'm going to model, the first is butadiene. Okay, so the butadiene, so we as I mentioned, a separate tab is there available which is a group contribution tab, though you can use anywhere else which is available. A whole periodic table is there, you can take it out and use it depending upon the requirement, but for today's this tutorial I am going to be using the group contribution tab because it will have the chi parameter available within it, so I won't have to calculate, though I will be showing all the options for the calculation of the chi parameter. So we are creating a butadiene. So to create a butadiene, what we have to do, we have to use the group contribution tab here. So I am going to drag and drop this CH2 double bonded molecules, and then again to CH2 CH2, and then the terms. Okay, we are going to use the single bond between these and double bond here, and we are done with creating the butadiene. So we can adjust it to make it look horizontally. Okay, so butadiene is completed. Similarly, we are going to model the styrene. Here in the styrene, again the group contribution tab. So drag and drop, use the CH and one CH2 terms, make the bonds. So once you are done with the modeling of the styrene and the butadiene, next is to create a file under the DPD modeler. So both options are there, either you can just click on it and it will open up the working directory where you are working. So let's just name it as ST and BT, butadiene. Okay, so this is the phase separation calculation will be done between the styrene and the butadiene. Next is to import them and to register. Multiple option, either you can drag and drop, another one is you can use the register option. Okay, since we are importing the monomers, you can choose. We have imported the butadiene, next is the styrene. So here we have added. Okay, we can model it here in the working directory. Let's just take 10 monomers of each and select them. So we have modeled the polymers of the polybutadiene and polystyrene as well, having the monomers of 10 as a polymerization. And now we have to get the values of the segment molar volume, as I mentioned, the cohesive energy and the solubility parameter. These are available under the databases KRI, NEWA, Fedders, Dunkel and Hofzer. So let's just I have chosen the Fedders. Click on set, and as you can see, the values is been fetched. As I mentioned, the reason to use the group contribution tab, because it contains the values which will be required for the calculation of the chi parameter. Okay, so this was done for the butadiene. Similarly for the styrene as well. As you can see, all the values has been fetched and been properly added. If you click on the properties, you'll be seeing the whether it is a polymer or a solvent, the terminologies, terms. Here we have added as a hydrogen. It will be replaced by in the calculation as a H, hydrogen, and segment molar volume, number of the monomers, then consideration for the dimer or the monomer for water molecule if it is available, otherwise not. If you want to consider the frozen core method calculation, then you can click on to on or make it as off, really for both the cases. Next is we have to make the segment molar volume as a comparable value. As you can see, for the styrene it's 86.5 centimeter cube per mole, whereas for butadiene is 59.2. They are not quite comparable. So to make them comparable, what we can do, we can increase the number of monomers. If you can see, okay, make it 2, 3, it will become 3 times of the each monomer of the butadiene. It will become 177.6. and once you change the number of monomers, you have to update the structures. Okay, so once you have updated the structure, it will stay there. Similarly for the styrene as well. As you can see, twice of the monomer of the styrene will make up about 173 centimeter cube per mole the segment molar volume, and again update structure. Okay, so this was for the database. But as I mentioned, if in your case your molecule or some atoms don't have any of these values, we can go on to calculating the other options by other methods, the Monte Carlo method, molecular dynamics and QSPR. Okay, the QSPR is a quantitative structural property relationship method. Okay, so we'll be going with the next option is the doing Monte Carlo method, where, as I mentioned, we have to apply the force field. Right now we'll be using the trading force field. Once this is done, we go to molecular mechanics calculations. The same steps as I mentioned in the molecular modeler, there we didn't do because again we had to repeat here. Okay, once this is done, you can visualize, same as in the case of and as you can see, we have taken the 3 butadiene monomers for this particular calculation to maintain the segment molar volume. Once this is done, we can to calculate the molecular orbital calculations, and here various or you can say multiple engines are available for the calculation of the molecular orbital calculation, which is a charge calculation: Firefly, Gaussian, MOPAC and MOSEMI. For this case, I am using the MOSEMI engine. You can check the requirement options or the various parameters here. Once you are done, you can see the various the charges available on each and every atom here. Okay, and this is some excess charge available. We can make it to nullify. Once we are done with the calculation of applying the force field, doing the molecular mechanics, molecular orbital calculations, this will be utilized into the segment pair. Okay, so this step is done. Then we go to segment pair, and here, as you can see, Monte Carlo method is there. Okay, right now it is grayed out. Okay, so for we have to do the calculations for it, since we have done for the butadiene. Similarly, we have to follow for the styrene as well. Okay, I'll just make it more fast forward. So this is also done. Similarly, molecular orbital. Yeah. So we have calculated the applied the force field, did the molecular mechanics calculation, minimization, molecular orbital calculation for both the monomers. And once we come to the segment pair, then as you can see now it is active, and you can use this option to calculate segment molar volume and the cohesive energy and the solubility parameter. So these can be calculated. Okay, so we have done with this here. The next is the molecular dynamics method for the calculation. Again, if you click on to here, as I mentioned, it will require a pre or simulated amorphous structure of a butadiene. Okay, so you have to prepare a butadiene structure that could be generated under the polymer modeler, and there we can create this and put the input file here and the simulation conditions. Once you are done with providing the amorphous structure and the simulations condition, you can click on to start, and once the calculation is completed, you get to calculate the solubility parameter. Okay, for example, here you can choose the last 10 records for the calculation of the molecular dynamics, and if you want to delete the intermediate files, you can just keep it on check. And for if you want to consider the electrostatic interaction, the charges between the monomers, then you can keep it choose either the cutoff for the Coulomb or the Ewald interaction, and cutoff length here you can define it. So once you are done with the calculation, you will have one input file containing the data of the cohesive energy and the solubility parameter for each section. Similarly, for the styrene as well, we have to follow the same. And in the group contribution QSPR, which is a quantitative structure property relationship, this is a separate option available, and these options can be updated, the data for it, which will be done under the deep QSPR method. So the various options are available to get the values of here. So for that case, we are again using the FEDERS database. The temperature, just click on OK, and it will calculate you the length of the monomer, segment molar volume, cohesive energy, and the solubility parameter. It has calculated. Similarly for the styrene as well. Okay, so this is how we calculate for each segment the cohesive energy and solubility parameter. Next is the calculation of the chi parameter, which is an Fleury-Huggins parameter, and as you can see, various tabs are available for the calculation of that. Okay, so in the group contribution method, as I mentioned, it will be using the database. You have to just click on to calculate all pair, and it is going to calculate the chi parameter for you at the 300 degrees Celsius for basis molar volume of 100. Right now, as you can see, this basis molar volume is 100, whereas if you see here in the properties, it's around 173. So you have to take the average of the segment molar volume into the segment pair as well. So let's make it as somewhere around 175 it would be. If I calculate, then this is our chi parameter. Okay, so if it was done for the group contribution method only, so we would have gone for the generation of the input file, but since I have to show you all other methods which are available here, so the next option is the Monte Carlo method, where we'll be calculating the coordination parameter for each segment and the energy parameter. In the calculation of the coordination parameter, either we can calculate the all at once or the Z11, which means the segment 1 when it is in contact or nearby to the segment of 1 again, and 1 with the 2. So if it is nearby, it will calculate those coordinates for it. Okay, so I am going to calculate it for all. The maximum configuration of the trial is 2000, evaluation calculation 10, and output interval as 100, and random seed you can choose as per your requirement. If I click on to calculate pair, in the console section you can see it is calculating for all the pairs of the coordination number. Once this is done, and even it is calculating for energy, since we clicked on to calculate all pair, as you can see it has calculated for the energies as well. So this is the coordination number that has calculated, and you have to make sure that these coordination numbers should converge properly. So for that case you have to choose the appropriate number of evaluation. Okay, so similarly as in the case of here also, once it is done you can see the values here. You can even plot the histogram for various temperatures, and the width of the histogram accordingly you can check it. So yeah, so once this is done you get to the Monte Carlo method for the calculation. Okay, so again you can to define the temperature and then click on to calculate for all pair, and it will calculate for you the 0.52247, the chi parameter, with the help of Monte Carlo. And as you can see by graph, so you can plot it and see either you can go with a weighted value or the averaged value. And the text or the data formats are available under this particular file. You can check it. If you want to use it separately, you want to plot by yourself, you can also do that. So the Monte Carlo method has this way, these were the steps that is to be followed for the calculation with the help of Monte Carlo. The next option is the fragment molecular orbital calculation method, which is more accurate than the simple Monte Carlo method. Here again we'll be giving the calculations and we'll be calculating the coordination number and the energy for all the pairs, for the energy as well as the coordination number for all the pairs. If I click on it, another tab will open up, under which we get to decide if you have a server available. You get to run your calculation of the Z and E for all the pairs over the server. But since we are running locally and the engine we'll be using is the Abinet MP, the maximum or the total number of core which is going to be utilized you can mention over here, and the number of jobs to be run on each core parallel number of jobs. Okay, so 2 jobs will be running simultaneously, 4 on each core, that it will be separated. Once you have good to define, then you can get to click on to calculate the coordination number, and then we calculate the energy. The same procedure we followed here under the Monte Carlo method. First we calculated the coordination number and the energy parameter. Similarly here, but with at quantum mechanical simulations with the help of the Abinet MP engine available here. Okay, so it is more accurate and more reliable method to calculate the chi parameter. So the first option is to calculate the coordination number. Just click on to coordination number and it will start calculating the Z values for all the pairs. Once it is done, it will prompt up and you can click on to calculate the energy again. But again, this is a very expensive calculation. It is going to take a lot of time for the calculation, since being a being the quantum mechanical calculations. So we have to, if you have a available computation power which will be suitable for this calculation, you can go through. Otherwise you can take the interaction parameter and the chi parameter from the published papers as well, and you can input those values in the coming when we are going to create the input file for the DPD modeler. I will show you there how you can use the published data here into the input file of the DPD modeler and you can replicate them here. Okay, so we'll wait till the calculation of the coordination number completes and I'll show you the calculation of the energy as well. So we are done with the calculation of the coordination number, and as you can see we can now calculate the energy as well for all the pairs available. If you click on to calculate the energy, and it will prompt up the energy calculation has been started, and we can check the progress by checking the check status and get results. This option is available here. If you click on it, it will prompt and it will say it's like it is going to calculate for around 6002 times for all the monomers or the segment that is been added here into the simulations. So as you can see, it is going to take a lot of computation power and a lot of computation time. So for this particular conditions, okay, Once this is done, you can go on to the next tab, which is under the same, and here you can choose the interaction data, which kind of interaction data you want to use, and then you can choose either the isotropic evaluation or square root method, and then click on to totalizing results, and you will have your fragment molecular orbital method calculation energy and the coordination number. So I am going to stop this energy calculations. So this is how we get to calculate the energy parameter. The coordination number will be calculated since we calculated already there. Okay, the energies are yet to be calculated, which is again very expensive computation. So we had already aborted that calculations. If we had completed, so it would have been a working tab, and we would have seen the same as in the case of the Monte Carlo method, the energy 11, 12 and 22. Once this is done, you can get on to Monte Carlo method to calculate the interaction parameters. Okay, so this tab was, the first tab was just to calculate the energy parameter and the coordination number parameter, and later on to the next, again the Monte Carlo method for the interaction parameter calculations. The next is the molecular dynamics method calculations. Again here we can click on to calculate, and since we have not calculated previously into the segment sections, okay, because it would require us to feed the amorphous structure. Similarly, the same methods will be followed here as well for the calculation of the chi parameter. Then comes this mix system. For this as well, we'll be needing the amorphous structure again. So we have to generate the amorphous structure for this particular segment file first, and then feed that value here by giving the simulation conditions. Once this is done, you get to calculate the cohesive energy calculation for your particular segment pair. Once this is done, you'll have your cohesive energy, and then followed by the calculation of the chi parameter. And the QSPR method, again we can just click on it because it is using the database, so it will prompt the value of the chi parameter. So once you are done with the calculation of the cohesive energy and solubility parameter, once you are done calculation, you can go on to segment parameter to calculate the chi parameter, and you have already modeled your polymer. The next option is to create the input file. One more thing, suppose if you have multiple formats or the multiple types of the polymers to be incorporated, you can use the option available here to create a new polymer, and one more tab will be available where you can model it separately in a different manner. Okay, so that can be done. Once this is done, you get to create the input file for your for the DPD modeler engine to run for the simulations of the phase separations. As you can see, multiple tabs are again available here: the simulation conditions, interaction parameter, bond parameter, angle, molecule, and others. So there are other options are available. I'll explain each and every one. The first one is to calculate the number of water molecules depending upon the basis molar volume that we had created. If I click on it, as you can see, it is saying the 9.68 number of water molecules should be considered for the calculation of this particular case. But as per the manual, it should be around somewhere 6. Okay, if you click on it, the other values, for example the unit time step and the unit length, will be updated accordingly, and we can choose which method to be used. For example, either group contribution method, molecular dynamics, mixed system, or QSPR. So as you saw, various tabs are available for the calculation of the chi parameter. So depending upon the method that you have used for the calculation of the chi parameter, you get to choose over here. So we are going to use the group contribution method. Okay, so this is how we go proceed, and the delta T should be around 0.05, and the number of steps, maximum number of steps that is to be run for the OR simulations output interval, as I have always mentioned, it should be 1/100th of the total number of the steps to be followed, and the DPD algorithm parameter should be kept as a 0.65 by default. The next is the interaction parameter. this is where very important tab. Okay, we calculated the chi parameter. Okay, the next is the interaction parameter. The interaction parameter is calculated on based on the chi parameter with the help of the option formula here. As you can see, various formulas are there depending upon the requirement and this condition you can choose as well. And as mentioned, all the methods are available, you get to choose here. We are focusing now the group contribution method, and depending upon the group contribution method, it has calculated the interaction parameter. Next is the bond parameter. Since this is using the DPD type of the bond parameter, the spring constant and the bond length has been automatically added. And if you want to incorporate the angle parameter, you want to enable the angle parameter and then you can put the values for the spring constant as well as the angle between the two segments, for example butadiene. Okay, and all the segments that we have added, and again from here we get to decide the number of molecules to be incorporated in your simulation box. Okay, so for example, again two options are there, either depending upon the molecular number or from the volume fractions also you get to choose. Okay, so from here also, let's just say I want, since only one pair is available, one pair of the segment is available, I am making as a 100% volume fraction. Okay, and we get to decide the cell size. For example, 20 angstrom is my cell size with the volume fraction is 1. So a total of 1200 molecules will be incorporated in your simulation box. Or we can get to decide the molecular numbers also. Suppose I want to add 1500 molecules into my simulation box, the cell size will be automatically calculated. Okay, so it's up to you, you can choose either way. Then the density output, okay, whether you want some density output or not, so you can you get to decide, either make it on or off. And the number of steps, interval, radius of the segment that you want, that can be defined over here. And the potentials, for example, bonding potential, non-bonding potential of 1 and 3, if you want to incorporate or not. You want to generate the coordinates by cognate or not. So these are all default, that should be kept as it is to generate the input file for the cognate. So these were all the options which are available for the generation of the input file of the DPD modeler. So once we are done with the applying all the parameters, you get to create the input file. So our input file has been generated, and then we get to see, if you click on to the cognate modeler, as you can see, we have added the number of the segments of 1500 as we mentioned into the creation of the input file. Okay, so we have generated our input file for the DPD modeler. The next is, again, as we have already applied all the conditions of the total number of steps, output, interval, and the solver as well. Okay, DPD we are using, and then we get to run our simulation system. And here we have to we can choose the engine. Okay, so we are using the cognate engine. We get to decide number of parallel, and we'll wait once the simulation completes, then we'll be able to see how this phase separation structures form. And depending upon the chi parameter that we have calculated by various method, various options which is available under the DPD modeler. So once our simulation is complete, let's take out the output file. And as you can see on the right hand side, you get to see the various parameters. For example, the total energy as the time progresses for the particular simulations that we have ran. For example, you can check the total energy, Hamiltonian energy, kinetic energy, potential energy, density. Now since we are running the DPD, it is going to be constant. And even you can choose the x-axis as well, for example either in time frame, for example picosecond, nanosecond, or milliseconds, or the tau, which is by default. And as you can see, as the interaction parameter was calculated with the help of the chi parameter that we calculated by the various method that I shown in the DPD modeler file. And as you can see, depending upon those values, it has been generated. And even we can see all the frames, how it has been moved from the randomized structures to the phase separated structure, where the same or the like affinity molecules having more affinity are gathering towards each other, whereas the less affinity molecules are getting separated, which is again forming a channel like a structure. As you can see, the red molecules are trying to gather at one particular as close to each other, whereas the blue molecules are trying to separate. So these are simulated based on the interaction parameter that we calculated. And to show you some other way also, we can visualize in an isosurface format as well. In the analysis tab, if you click on 3D density distribution drawing, then we can choose which molecule to target and to visualize. Let's just observe the butadiene, and you can choose the display option either in color contour or the isosurface. And the isosurface value, you can choose it here, maximum and the minimum value for the isosurface. And arrow scale, okay, we'll keep it as it is. Click on to analyze, and as you can see, it visualizes only the butadiene. And if we run the frames, and you can see how that structure formation takes place, the phase separation takes place. Not only this, but you can import as this particular distribution that we have generated here in various other formats. For example, triangular mesh, STL format, voxel mesh for the LS-DHIO. If you want to study its mechanical strength, then you can export the voxel mesh for the LS-DHIO as an input file, and click on to analyze, and it will generate an input file for you that will be utilized in the LS-DHIO engine for the mechanical property analysis. So this way, or you can create an STL image also, and under the even for nest and simulations also, voxel mesh can be generated, tetra mesh. So depending upon the requirement, we can create an output in such a way required for the next higher scale of the simulations. Okay, so this is also that can be performed here. So this was all about the DPD modeler and the various engines, various options, various methods that is to be utilized for the calculation of the chi parameters, and thereafter the calculation of the interaction parameters. Once this is done, we create an input file for it, and we run the simulations to observe how this phase separation takes place. Thank you.